So good afternoon, everyone. I'm Sujatra Bhattacharyya, and my supervisor is Professor Arindam Chakraborty. So today I'm talking about the spatio-temporal variations of moist static energy profiles, and particularly focusing on the monsoon season. So at the very beginning, we all know about this moist static energy. This mathematically can be written as this, like H, the moist static energy, is Cp times the temperature plus the geopotential Gz, and the Nq is the moisture related energy. And the first two terms represents the dry static energy, and the together three terms represents the moist static energy. And why is it important? Because it is just like equivalent potential temperature, it is conserved in the moist adiabatic process under hydrostatic approximation. So for the moist convective processes, this moist static energy does play an important role. So in the beginning, since my topic is on the spatial as well as the temporal variations of the moist static energy, I try to start from the diurnal time scales. Although I have not plotted for every hour how the moist static energy profile looks like, but I have just selected an event on 31st August 2023. So many systems are formed over this South Peninsula region near Bangalore and at this part. So I have chosen from the reanalysis data only, I have chosen this particular coordinate 13.738. I could have made I would say, an average, but still I have chosen one particular coordinate very near to Bangalore, and on 31st August 2023, and just plotted for 6 hours at 6 hours gap from 00 UTC, then 06, 12, and 18 UTC. The event actually started from at the evening time, and it continued till night. So if you look at the profile variations from 00 UTC to 06 UTC, then 12 UTC, which is 1730 hours IST. So you see that there is a change in the moist static energy at every level. You can see that at every level you will find that there is an increase in the moist static energy altogether from the lower troposphere towards the to the upper troposphere region. And it remained almost similar at 18 UTC, 1130, but yeah, somewhat becoming much more stable. That is more towards the lower energy regions. Next, if we go towards now from the diurnal scale, if we go towards the daily average kind of a scale, then or I would say hourly average or day-to-day variations of the moist static energy. For that, I have chosen another system, low pressure system, monsoon low pressure system. Particularly, I have taken the case of June 2019. We know that in June 2019, the onset was getting stuck near the South Peninsular India because of the weak northward propagation, but not northward propagation of the MGO-related PWAT anomalies. But this synoptic event has given us a good amount of rainfall, creating the onset over the central Indian region. So I've chosen this low pressure system, which happened about 20 to 22nd June. So just one day before, I have started 19th June to 20th June to 21st June. I have not continued further. So just to show that how the variations looks like at this particular average over this particular box. So you can clearly see that there is a strong shift in the moist static energy profile towards the higher energy regime. But in the lower troposphere, it didn't change much, but mostly the changes can be seen in the upper troposphere. So this is another variation which I wanted to show. Now, if we go from daily scale to the monthly time scale, so the first thing which comes in our mind is that of the climatological precipitation or the seasonal cycle of the Indian monsoon rainfall. So this is over the Indian land, IMD data. 1948 to 2021 for 74 years average, and this is how the seasonal cycle looks like. You all know this. July is the peak month of the precipitation, and July, August mostly are the peak months. June is stronger, but September is somewhat higher than that of the June, which is picked up in the seasonal cycle. But if I see it in the moist static energy profiles, very clearly from June, say this one, to July to August, a clear variation with the precipitation can be seen. But look at the September moist static energy profile. It is lower than, it is much lower than that of the June profile of the moistatic energy. So it seems that it is particularly in the monthly time scales, or if you go higher like the seasonal time scales, it is not only the moistatic energy profile which may contribute to precipitation. Might be some dynamics which the interaction with the dynamics, large scale dynamics, that can cause precipitating event. We will see that. Now, let's next go to the seasonal average case. And for the seasonal average means June to September average, which is the monsoon period, which we define. And what we can do, the temporal variations in seasonal average can be only the interannual variability, like year-to-year variations. And the way which we see that the variations of the moistatic energy is to categorize some excess monsoon years, some deficit monsoon years, like flood years, drought years. And let us look at the moistatic energy over the Indian land region during this flood and drought years. Again, clearly, this flood years in the lower troposphere up to 300 hectopascals, you can see that the total energy at each and every level has increased as compared to that of the during the drought years. And this is consistent with one of the papers, very early papers. They have used NCEP reanalysis. And even if you do for NCEP reanalysis, means reanalysis to reanalysis it may vary, but I have checked it for NCEP reanalysis, it does not vary much. It's quite a similar kind of a profile. Important to note that there are 12 excess monsoon years between this period and 16 drought years, deficit monsoon years. Now, what I did is that based on this seasonal monsoon standard deviation criteria for flood and drought years, I have categorized those flood years and drought years. And on those composite years, I have taken the monthly MSC anomalies. We are now earlier from the up to earlier slides, we were looking at the mean moistatic energy profiles. Now let's see how the anomalies changes during the excess monsoon years, each and every month during the monsoons, and for the drought years. So clearly the moistatic energy anomalies is positive during the flood years, and in the drought years it is negative. Look at July. It's positive but weak, and this weak positive anomalies of moistatic energy can be exactly similar to that, can be connected to the precipitation anomalies. If you look at the July precipitation anomalies for all those flood years, you will find out that the precipitation anomalies are very weakly positive as compared to the negative anomalies of the drought years, the precipitation anomalies. So it is somewhat following the precipitation pattern. And another important thing to note, all figures looks almost similar, that for the flood years, it is the MSC anomalies are positive. For the drought years, it is negative anomalies, it is showing. But look at the variation here in September. Such a strong variation between a drought and a flood years, or I would say the interannual variation is very stronger in September. So what might be playing a role, we will see. But before that, let us take a look quickly at the temperature variations, the same way, temperature anomalies during the drought and flood years, and I will show the moisture anomalies as well. So during the flood years, in all these patterns, you will find out that the lower troposphere is having lower temperature. Drought years has higher temperature, might be because of the deep clouds during the flood years that has cut off the solar radiation, the surface temperature, or near the surface, the temperature drops down. But why is it increasing here? Because of the clouds, the condensation process, the latent heat will be released, and that can cause this temperature to rise. You get some positive anomalies. Here also, it's not positive, but it is showing a similar kind of a pattern, like it is going more towards the weaker negative anomalies, and it's increasing with that. So this is a similar kind of pattern. And again, you can see that temperature variations also in September is the strongest. Let's look at the specific humidity. Relatively at the lower troposphere, you can see that somewhat weaker, but after that it starts increasing, and then it starts decreasing again. This may be on account of that in the flood years. It's possible that
defining flood and drought with JJA or
JJAs.
Separation.
No, JJAs I have defined.
Separation.
Okay.
Because the distortion is in July. Because you're taking JJA flood.
Right.
That July may not have been flood.
Okay.
Okay. For each month, choose 10%.
Right.
It may come out differently.
Right.
Otherwise, it's very puzzling. Why July is so distorted?
Yeah. Okay.
Right.
Fine.
And see, September, you'll see in the last 10 years,
Yes,
September flood years are very strong in the last few years.
maybe.
And that shows up in that.
Yeah, maybe.
Yeah.
Fine.
So you want to each one independently.
Right. So the September variation, we have seen in our work only that September variations are mostly related to the NEO 3.4, the ENSO's variation. And if you look at the moisture flux convergence over the Indian domain, you will find out that the N34 regressed, the NEO 3.4 regressed or ENSO regressed moisture flux variability is strongest, the FNet is strongest during the September as compared to any other months. Maybe those variabilities are because of the ENSO related variations. Now, let's see the contrast between the land and oceans, the MSE profiles, particularly over Indian land, only the land regions, 8 to 28 knots, 70 to 90 is the entire Indian region. And Bay of Bengal, I have intentionally chosen somewhat northern latitudes, 10 to 24 north and 80 to 100 east, only the oceanic region, because we get most of the precipitation over the Bay of Bengal, particularly in the northern parts of the Bay of Bengal. That's why I have chosen this. And if you look at the moistatic energy profiles, very clearly you will see that much stable profiles can be seen over Bay of Bengal, the atmosphere over the Bay of Bengal, whereas over the Indian land, it is somewhat less stable as compared to that. Now, if you look at the temperature variations, it looks similar. In the moisture variations also, it looks similar. But then what happens to the fact that during the monsoons, the land surface temperature is somewhat lower, cooler than that of the oceans. Yeah. Right. Right. In the reanalysis data, we generally get this. I have validated. So this is surprising thing. Yeah. Right. Exactly. Exactly. Because it rains much more over the northern Bay of Bengal. Right. Yeah. But what in the subsequent slides, I will try to explain that how we can get a very strong rainfall over the Bay of Bengal based on some previous papers. So let me just try that. No, this is ERA 5. ERA 5. So yeah, so that what I was talking about, that during the monsoons, we know that the land surface temperature is generally cooler as compared to that of the oceans. That's why the land ocean contrast theory fails and we go towards the ITCZ, the framework. So, but it is visible here also if you look at the surface temperature over oceans, because the surface pressure over the ocean region is higher. So the surface temperature is somewhere here over the Bay of Bengal. But the surface temperature of the land is somewhat here. So you can clearly see that there's some in temperature, you will see very little difference definitely, but the difference exists at least at the surface. But after that, I'm not finding in the, at least in the reanalysis, I'm not finding much of a difference between the land as well as over the oceans.
No, you should point the difference. Whenever you are plotting, because the range is so large.
Yes, yes.
You have plotted a difference.
Yeah.
Because the difference is not seen because the range is too large.
Right, right.
Right?
Right.
So whenever you have vertical profile, you plot the diff, you bring out the thing.
Correct. Correct. Okay. Now that is what I was exactly trying to make out, that the precipitation over the Bay of Bengal region is very, very strong, but as compared to that over the Indian land, it precipitates hugely over these northern parts of the Bay of Bengal, the latitudes which I have chosen. Then what might be the possible reason for that? So I looked at the profile of vertical velocity, omega. It's very strong. The omega profile looks very strong over the Bay of Bengal. The ocean is the Bay of Bengal region only, the same region. And over the land also, it is stronger, it is negative. Ascending oceans can be seen, but comparing the oceans with the land, the ocean vertical profile is of the omega is much stronger as compared to that over the land.
And you should check whether the diurnal cycle. See, in the land, there is a strong diurnal cycle. Ocean, there is almost not much. That may be affecting your mean.
Yeah, okay.
Because diurnal cycle over land is very, very high.
Yes. Yeah, I have to check that. I have not seen that. So I have actually looked at this particular paper by Guan et al. They are trying to understand using vertical advection of moist static energy and over the West Pacific and the East Pacific Ocean. And they're trying to come up with a particular theory. I'm applying that theory here. Let me just show. So what I have plotted is that instead of integrating the omega delta H delta P, I have plotted at each and every level over the oceans, over the Bay of Bengal, and over the Indian land. So if you look at over the oceans, you will find out that the omega delta H delta P first becomes negative and after that becomes positive. This is happening because of the shape of the moist static energy profile. It first decreases with height and then increases with height. So because of that, because omega is almost negative, always constant throughout the levels. So this is happening because of that. Now, it is the if you now vertically integrate this particular or at all levels, then what happens is that it is actually balance between the positive part and the negative part. So what does this positive part showing? The positive part shows the export of dry static energy or moist static energy or dry static energy, I would say, because upper troposphere you generally have the dry energy, not too much of moist energy. So there will be a strong export of moist static energy or dry static energy at the upper troposphere, and there is a less compared to this. There is a less import of the moist static energy at the lower troposphere. Now, if you integrate over the Bay of Bengal region, you find it the vertical advection integration comes up to be plus 50 watts per meter square, which is very strong compared to if you integrate over the land. Both are positive. So what does it say? Means my interpretation will be that there is a huge export of moist static energy from that particular atmosphere to the surrounding region, and comparatively there is a less import of moisture. So it is trying to stabilize the atmosphere there. And what is the convection process? The convection process tries to stabilize the instabilities which are formed. So if there is a strong export of moist static energy at the upper troposphere, and compared to that, there is a very little import of moist static energy or moisture from the lower atmosphere, it is trying to stabilize. And the strength of the stabilization can be found out using this omega delta H delta P. And that suggests that because it is strongly trying to stabilize to its mean environment, there is a strong or deep convection, deep convective activities will be found over the Bay of Bengal, whereas over the land regions, the export, the rate of the amount of export and compared to the amount of input, that is very, very little. The difference is very, very little. And that's why you will find deep convection over Indian land also, but the strength of the convection is not that much as compared to that over the oceans. This is the way I try to interpret based on this study by Bowen et al. They showed that some deep convective clouds will be formed when there is a stronger export as compared to the less import of moisture from the lower troposphere. So this is a simple interpretation, and this export-import balance can be seen through the divergence of moist static energy fluxes, horizontal divergences. So you can see that there is a very strong divergence at the upper troposphere and little lower convergence of moisture in the lower troposphere, and that is causing that is trying to stabilize the atmosphere.
And what particular average compared to this, compared to the numbers? Those two numbers you put here.
Yeah.
For this, what are the numbers here?
Yeah, I have not looked at it.
What?
Yeah, I just integrated this part. I will check that. I have not seen that. So maybe this is the thing. Maybe the dynamics or the omega interaction with your moist static energy profile may lead to deep convective structures and precipitation more precipitation over the Bay of Bengal as compared to that over the Indian land. So that may be one of the reasons. Yeah. Okay, now next is the same precipitation plot. And what I have done is that I have just looked at the moist static energy profiles, how it is varying from say 10 north at 90 east. That is over the Bay of Bengal from 10 north, and I am heading towards 22 north, more towards the land regions. And you can clearly see that all levels, the moist static energy is increasing, tending to increase. Now, here we ask a question that this moist static energy, which is having a kind of 3D variation, if you fix the time, if you fix the time of the moistostatic energy, you have a zonal variation of moistostatic energy, meridional variation of moistostatic energy, and there is a variation with height as well. So can we reduce this moistostatic energy, the structure of moistostatic energy, into some certain parameters which only has some 2D variations, like only in the space, so that only looking at those parameters in X and Y, we will be able to talk about that what will be its shape in the Z direction. So that is what we try to find out after this. I looked at the dominant modes of the moistostatic energy with JJS average. The first mode is very strong. This is without removing the trend, but if we remove the trend also, it comes out about 79% strong. The thing to notice here is that if you look at the three dominant patterns, you find that there is always a non-constant, a constant kind of profile, a near constant kind of a profile, and you have a symmetric nature. And at the same time, you have the third mode, which is showing an anti-symmetric nature as well. So even if you look at the moistostatic energy profile, you will have some kind of, it seems like that there is some kind of an symmetry which is there, as well as there is some asymmetry. Here somewhere, sometimes it is larger as compared to the top, like that. So any questions? Fine. So based on that, we tried to make a mathematical function for the moistostatic energy, a simple mathematical functions, keeping in mind that there is an anti-symmetric part, keeping in mind that there is a symmetric part in the modes, and I have put a reference point as the moistostatic energy minimum value. So what does this mathematical expression shows is that there is a moistostatic energy H at some pressure level P is equal to A, which we are calling as a shape parameter. I'll talk to it later. So this is the A, the coefficient of the cubic polynomial term or the cubic term, P minus P naught. Now what is P naught? P naught is the level of the MSC minimum. Suppose this is the moistostatic energy profile. The minima is around 600 hectopascals. Let us consider for this moment. And this is the MSC minima. H of P naught will be this value. Right? And okay, now B into P minus P naught whole square. So some way there is a symmetric term, there is an anti-symmetric term, and there is a moistostatic energy minimum. Now you need A and B. We don't know what is A and B because A and B we need to fit the profile in vertical axis. So what we did is that we plug in two values, say 150 hectopascals at top level pressure over here. We take the value from the reanalysis data. Similarly, for the bottom level also 950 hectopascals, we plug in the value and try to have two equations with two unknowns, A and B. We can calculate that from this particular thing. And if you look at the fit using this particular mathematical function with the original one, you'll see that it roughly fits the moistostatic energy profile, particularly at least over the regions which I have shown, like 10 and 22 north. It fits well, but yes, these variations it couldn't capture. Definitely will not be able to capture because it's just a mathematical approximation. Important thing to note is that the moistostatic energy minimum value is coming from us, from our side. We are inputting it. So this is fine. There is an increase. Definitely, we have seen that in the previous profiles. But there is a change in the shapes as well. And that can be seen from these A and B values. Where there is low moistostatic minima, you will find that there is a higher values of A and B correspond to with respect to when you have larger moistostatic energy minima, you have A and B values lower as compared to this. And some model constraints are there, like I have put the bottom level pressure as 950 hectopascals. If it is less than that, the surface pressure is less than that, we will not be able to fit properly. So those regions I have intentionally eliminated from the next few plots. And places where MSC minima is larger than 650, this thing, if it is 700 hectopascals for, if you take 700 hectopascals as your P naught, then it does not fit well. It's a limitation of this equation. So based on that, so okay, fine. Three parameters therefore, MSC minima, the A and B. These are the three parameters which are varying in the 2D space, and we can comment based on that, that what will be the moistostatic energy profile variations from one place to another. That is what I'm trying to see. This is from the observation. So I've just plotted the MSE minima, and you can see this is a comparison between a drought and a flood year again. And clearly the moistostatic energy minima values has increased more towards the northwest India. This is how we see, even in the precipitation also, we see that more to the west in the flood years, the precipitation pattern comes. So this can be seen. This is from the observation, it's nothing new. We haven't done anything here. This is the scale parameter. These white patches are those regions where there are the constants. So I have removed all those regions. You will not find the orographical regions here, Western Ghats and all these places. And okay, now if you look at the drought and the flood years and the variation of the B, this is the scale parameter, the B value, the symmetricity, I would say. We should be looking for, because since the moistostatic energy minima has increased in the flood years, we should be looking for lower values. And if you look at the drought to flood years, you can see that over these regions, there is a stronger or lower values of B, which can be seen. Even over here also, much less lower values, I would say, much higher values, I would say here, but this consists of much lower values. That shows that the moistostatic energy has increased for this particular regions. So in some sense, it is giving an idea that how the moistostatic energy profile will change with these variations in the space, with the variation of those parameters. And this is the shape parameter. This is not much difference, but here over this region, there is some differences, but it will not give much difference. It is just for shaping the thing. It will give you some kind of an antisymmetric push to the moistostatic energy profile. So it will not be much varying, but majority of the variation will come from this scale parameter, the symmetricity of the profile. Okay, now what can we do with this is that you have this equation. I've written delta P as this, and you can calculate, you can interact with your dynamics like your V, U, V. You can take it from reanalysis and try to calculate all these things, advection terms. And there is vertical advection of moistostatic energy also you can calculate. It's very easy to calculate from here, delta H, delta P. So in the vertical advection, you will not get the H of P naught because this is a constant quantity, H of P naught, the MSE minimum. So it reduces down to the contribution of the A, the shape parameter, and the vertical advection due to the B, the symmetric parameter or the scale parameter. So I just wanted to show, this is the last slide. This is the actual minus omega delta H delta P. I have made a negative sign here. So the profile entirely changes in this way. 10 naught and 20 naught based on the actual reanalysis data. This is the observation. And this is the from what you get from the vertical advection using this mathematical model. Scales are somewhat different. I should have made it in the same scale. Scales are somewhat different, but you can see that it also ends, this profile is peaking here, this 0.06, it is also here. Although it couldn't capture this part, couldn't capture this part, but these parts are well captured. Some parts couldn't capture, but some parts roughly, if you look at the entire profile, it is capturing the vertical advection of the moistostatic energy quite well corresponding to this. Little bit undulations couldn't be captured here. And if you look at that, what is the contribution for the, from the shape parameter and the scale parameter, you will see that mostly it is following the B contribution, this one, this part is following this. And A from the A's parameter, like the first term, it is somewhat lesser. The contribution is less. But what it is doing is that it is increasing the vertical advection of the moistostatic energy here in the lower troposphere, but it is trying to oppose in the upper troposphere. It is trying to oppose with a lower value as compared to this. So it is trying to reduce this region. So these are the things which we can do. Like you can do some mathematical expressions of the budgets or vertical advection or the horizontal divergence of the moistostatic energy based on this particular profile. So you don't need to look at the moistostatic energy profile everywhere. Reducing that to certain two parameters, we can easily fit something, and we can talk about the vertical advection and comment about the convective activities. So that is what we have tried to do. That's all. Thank you.
From
Which one?
here, it will be more divergence into the upper levels for deep energy. But if you see, is there more components from much of the from the local source like surface?
Evaporation. Surface evaporation you're talking about. Yeah. Over the Bay of Bengal, you can see surface evaporation is much stronger than over the land. 4.69 mm per day. So yeah, that is also maybe contributing. Yeah, sure. But in fact, the mean profile also, if you look at the lower troposphere is mostly controlled by the evaporation only. So if you look the mean moist static energy also, so the lower part of the moist static energy is stronger nature. The moist static energy comes from the evaporation, from the surface evaporation as well. So that is there. It is there. It's consistent. Yeah.
Last form.
Yes.
The partial derivative of the WH, right?
Yes.
So that if you integrate, it should be zero.
Yeah.
So this is somewhat to be that direction. Also, if you're chopping off the proper path, somewhere I don't know where.
Yeah, it will. Yeah, continue.
So maybe last form. Is partial derivative of omega h.
Yeah.
Divided by t, right?
Yes.
So that if you integrate, it should be zero.
Yeah, it is zero. Yeah.
W is zero.
Yes. Yes. Yeah, maybe. Right. Yeah, sure. Correct.
It won't be zero, Bala, because the surface fluxes are non-zero in this case.
So right at the bottom.
Yeah, the bottom it is non-zero.
Right. It is zero.
Okay.
No, this is so it is unlike mass flux that from surface you only got this one. So that the surface also will have a non-zero flux. But at the top of that atmosphere, the particle flux is zero.
Yeah.
So they are coming in not be zero. It won't be zero.
Yeah, but still, if we integrate.
Give a better sense of,
Yes.
okay, this is the flux that's coming from there,
Mhm.
and that's the upper boundary, you know what is going to come from.
Yeah, but you can check it. Is it?
Yes. Yes. Yes.
It's okay, but I was just thinking that if you change the different levels from 150 to say 200 or something like so you give your values and then
Here or that?
that age electricity will be
Okay.
whatever trend you show like for 5 years you get lesser whatever you're getting the trend of the values for AMD. Is it the difference between the levels, that pressure levels, is it also like have you done that analysis?
By changing the pressure level at the top. I have tried with 200 hectopascals. It won't change much, but I have not gone before that. Means 100. Yeah, similar. It's similar. Yeah, you will get that fit nicely at least. Yeah, that I can.
Regarding the moisture energy, the unexpected values in the Bay of Bengal, I just want to comment you that you can also look at the forecasted terawatt data set because there is one paper like incentive which is actually saying that on a diagonal time scale you can look at the moisture profiles. So there is a discontinuity data set, PNS data set, which is actually affecting this low level values, which may be
I'm sure that in the diurnal timescale it will come greater over the Bay of Bengal as compared to that of the ocean. I'm sure, but I think in the seasonal average something happens which is not.
Can the moisture for Bay of Bengal compared to the Indian land?
Mean profile I have shown.
Yeah, so mean profile. The moisture must be where is the moisture? Yeah.
Skewed.
Oh, okay.
Yeah, it's
Even upper level moisture are made. Right? That's what you were saying. Mean that's the mid level. So 700 milliwatt to say 900.
yeah, usually that is strong.
Okay, thank you. So that was a nice presentation, and I hope we'll hear more about that work later. So by the end of June, Monsoon had covered the entire thing, but notice that it moved rapidly after the early onset, and here it hung around 19 days, okay, and then again rapidly it went. So a very interesting sequence of transition, and that also clearly comes out in the all India rainfall. We started early onset, and then it was good. Then there was a long hiatus here. It was below normal climatology, and then it has continuously been almost above normal. That's why June came out above normal. And if you look at the core monsoon zone, it is even more clear. After that hiatus here, it really has picked up. This is the climatological where you can see it's well above climatological most of the days. So that's what has enabled the monthly mean now to overcome all this long delay that we had after the onset. And if you look at various zones, all of them are similar except maybe south, okay, where we had early rainfall and then no rainfall. But all the other parts, the south and east look a little different curve from northwest and central. Okay, not surprising. Central and north should go together pretty much. Now here is a summary of June. We have gone 9% above normal. Okay, the only prediction made was by climate, which I discussed in the first discussion. It was so they're way out. Even allowing for error bar, they're well outside the error bar. But in the case of climate, I will be very frank. I don't think they have any special technique. They make some forecast. They don't tell us how they do it. So there is bound to be a lot of error there. And so we'll watch their monthly forecast for the next 3 months, how they do. Here, what I want to notice is this is large negative, large positive. See, the difference is huge. And of course, country as a whole and south also there is a clear difference. Now, I also want to look at OLR, because OLR very often becomes a proxy for rainfall. It's an independent way of looking at it. What's interesting is that, I don't know what this is. This is showing that over the Arabian Sea, the rainfall was not much. So I don't know what it means. I don't understand because all the moisture is coming here and it is not raining here. Okay. And of course, we have the very high rainfall over Gujarat and Rajasthan. That's why the OLR is negative. But look at this region. This is Indonesia and parts of Pacific here. It has been raining a lot here also. But this part also interesting. Just to the east of China, there is a lots of sinking motion. Okay, for the whole month. Now, this is the data put out by IMD, which I like very much. Nice color rendition, showing that the big picture for July is this whole region was negative. Coast was okay or above normal. This was well above normal. This is the pattern that I think nobody captured. Pattern of very high rainfall of Gujarat, Rajasthan, and part of Madhya Pradesh, and a large negative pattern here for the whole region. Okay. So this is one figure that's put out by IMD. There's one more figure which is similar to this, but not so neat. Same figure put out as a part of the monthly mean. And by and large, you get the same thing. Only slightly, that looks much easier on the eye. I don't know why. This looks a little more complicated. Now, I'm going to compare with what is put out by a website called Agriculture Weather. Okay, the interesting website. So they are putting out their, I don't know where they get the data from. So they are showing this clear what we saw in the other picture. But this is somewhat crude. I think the data is not high resolution data, but pattern is almost same. And this is percentage departure. Now, this one is not a good way to do it. When you use point departure in this kind of plot, regions which are very dry, you get a high value like this. So that's somewhat misleading. So it has advantages, but in regions of low rainfall, it will show very high percentage departure. Now let's compare the monthly mean observation with forecast. Forecast is probability, so we cannot really compare 1 to 1, but clearly the forecast of CFSV2 and all this region of negative completion. Okay, I would say they got part of this right. Okay, but this one they completely missed. And now I'm going to look at a close-up. This is as put out by IMD's hydromet. They put out this thing. Sorry, this is put out by Regional Producer Center Mumbai. This is put out by hydromet. Now, why I want to show you, it's the same department. And I assume the rain gauge is same. But there are clear differences. Yes, see, this Solapur, but when it is not a Solapur, is showing deficit here and normal here. That I don't understand. How can the same agency with the same rain gauge put out two different results? Somebody has to check it out. And maybe this was put in by the Mumbai, this one, maybe they had more rain gauges of their own around. Okay. But that's one part. Second part is more complicated. This is between state rain gauge put out by the Karnataka Disaster Management Center, and this put out by IMD. Okay. Now there are differences here also. And here you can understand because it's not same rain gauge. And so some of these features are not similar because they're, of course, the scale is a little different. But you can see some of these high rainfall are not quite captured here. So this, and remember, this is very interesting. This is Davangere. It's 60% above normal, and I don't see a corresponding, it's not marked here, but it's one of these. I don't know how to, yeah, one cannot compare them easily, which is mixed, but it's not marked. So this is a different between two rain gauges. So that one has to, as a matter of fact, I know that during the Kaveri water dispute, the data provided by this and IMD, they don't agree. There's always a dispute on that in the court between two for government, okay? Now let's look at the All India forecast, which is my favorite. And you can see that from 19 June to 28 June, it correctly got the decline and got roughly the increase and the decline correctly. But this was wrong. June 28, it really got it totally wrong. But overall, I would say that All India rainfall is roughly right. And especially a trend. Actual value still one can debate about errors that's coming in. Now next, see the next 10 days here, up to 1st July, up to yesterday. Here I would say they didn't do so well because you can say, for example, 1, 2, 3, 4 days, very good. 4 days, not so good because they are all predicting. And 2 days, they are underpredicting. So to me, I wish I had data for different homogeneous regions. Then you can figure out maybe sometimes you got the right answer for the wrong reason. That possibility is always there. So I would like to know whether on these days the right answer came because there was cancellation between different regions, and in these days it didn't happen. So I hope one day I'll convince them to put out this for every region. Okay. Now this is the forecast for the next week. And the good news is that it continues to go. Have a dear, right? I think not in a touch here. No.
I think it is network issue.
Restart. Something got. Okay. Yeah, so it predicts above normal up to coming July. Okay, today is second for 5 more days. Then a slight decline the next few days. Yeah. Now this is the forecast given by AMD for this week. It's all over. We don't worry. Look at this week. It shows continuously more rainfall in this region for next 1 week. And this consistent you will see with all the other forecasts. For example, this is ECMWF. This is for this past week, which is correct. This is the present week, showing the right tendency. And if you go further, this is the coming week. You can see this slightly reducing size, then increasing, and finally it sort of disappeared. So the prediction of this is a good model is by 14 July, pretty much the high rainfall thing will disappear. Okay, but look at the interesting feature that you do. All across, from India to Southeast Asia, all the way. So it's worth understanding what the connection is between the regions which are obvious to regions of descent. Okay? Let's see what happens in the next week. Now, this is from the agriculture forecast group. And again, like last week, there's a difference between ECMWF and especially over Pakistan. Okay? This is very interesting. We can check next week whether Pakistan really got heavy rain or not. If Pakistan gets rain in the coming week, that means they are right. If they don't get, then GFS is right. So we'll just remind me to make sure that we check it next week. Okay. Now, this is a forecast that is made by IMD in the end of June for July. Okay. So July forecast is interesting. It has more structure than for June. There's going to be heavy rainfall here, near Orissa and other places. Strong deficit in northeast. Okay. So let's see whether this point comes right. But overall, they are claiming 106% for July. Okay. So we'll review that after 1 month, whether they get it right. But I'm always interested in the pattern. That this pattern will be correctly predicted. Okay. And well, about that, Arindam, am I right? That Agni Sengupta is going to give a talk on 7th July, right? Morning. Because he is in
8 morning. 8 next day.
8 morning here. Yeah, 8 morning here. He's 7th night. He's in California. So it will be 8 morning at 10:30. And he will discuss what I talked about, that Nigam and Sengupta, this one. So make sure you attend it and you'll get some idea about how his method works. And he's going to discuss both over India and over US, right? He's going to discuss his method. He's applied it both places. Okay. And what's interesting is he's applied it to summer rainfall in India and winter rainfall in US. So it's a little different. It's interesting. It's not monsoon, there's something else. But he still gets interesting signal. Okay. Yeah. So one more thing I wanted to check about these forecasts. So Goa is a good choice. It's one of the smallest states in India. Its population is 1/10 of Bangalore. Okay. It is just 60 by 60 kilometers. That's all. Okay. Essentially 1 or 2 grid points of a typical model. Okay. And this is rainfall on one day, I think it's 1st of July. Yeah. And then what I want to see, such a small area, see the range of rainfall. So they have, for a small area like this, they have 14 rain gauges. And the lowest rainfall here is, I think there's no data available here, 3 places. Lowest is 5 millimeters, highest is 128. Okay. There's such a large spread. Now, this clearly highlights the importance of more rain gauge density. Even having 14 rain gauges in a 60-kilometer box is not enough because Goa has got orography. The Goa's problem is that along this line, it's a coastline, and the mountain starts here. Okay? So for example, this thing is here somewhere, and the other 100 millimeter is here. These two are right close to the Western Ghats. This is around the coast. So one can see the large difference here, no problem. But I'm curious about in the plains of Goa, there is a difference of 58 to 5. That is very surprising. In the plains, where there is no orography, there's a large daily rainfall. So this shows how tough rainfall prediction is from models because there are large spatial variations for daily rainfall. Monthly mean it may average out, I'm sure. Now, this is the orography I wanted to understand. The mountains are here. And the two rain gauges, which give 1 millimeters, are right here and here. And all the other rain gauges are around the coast. So this kind of area is very tough to predict. And that's why you need more rain gauges and more radars. And Sujatra tells me next week it'll be Ambuj. So I am sure you'll talk more about this. Okay. Thank you. Yeah.
Okay. By IFT for a moment.
What?
I mean, so for diamond.
Yeah.
Oh,
They give it July number 2, I don't know why. So, but July, IMD would have just come, but June only 7 days. So I don't know.